this video, we're going to talk about product and quotient rules of derivatives as well as higher order derivatives. First up, we have the product rule. So this says that if I have two different functions, f and g, and I multiply them together, and I then take the derivative of f of x times g of x, this is the rule I'm going to use to find the derivative of that. So I just take the first function, multiply by the derivative of the second, add the second function times the derivative of the first. Let's work out a few examples. So the first one we're going to take is this function for h of x. Notice that I have two different binomials being multiplied together. So this one I'm going to identify as f and this one as g. Here are some things that I recommend you write out for the first couple times you do problems like this. So I identify what f is, and I identify what g is. I take the derivative of f, so that's f prime, and that's going to be 3 minus 4x. And I take the derivative of g, which is g prime, which is just going to be 4. And I set up my equation right here. So this is just the product rule. I take f, multiply it by g prime, and then I add g times f prime. So if I set up all of these things, I just plug them in and simplify. And here's what I'm going to get in the end once I plug everything in, multiply it, distribute, FOIL, combine all like terms. So that's going to be my derivative of that function using the product rule. And here we have another example of this equation right here, y equals 3x squared times sine of x. This may not look as obvious as the last one did, that we need to use the product rule, but this is like my f function, and this is going to be my g function. I'm going to repeat the same process as last time, and I have my f prime and g prime here, and I write out my little equation, plug everything in, distribute all the things, and then in the end, if I really want to simplify it, I just pull out a 3x because that's what's in common between both terms, and this is what I'm left with. And here's another example where it's a little bit more complicated and it has some other rules in it that we've talked about before. So our function here is y equals 2x times cosine x, so that's going to need a product rule, minus 2 sine x. So that 2 times sine x is just going to be the constant multiple. So the first thing that I do here is I'm just going to take the derivative of this part. I'm going to call that h of x, and I'm going to find the derivative of my f and my g to plug into this equation here. And this expression is going to be the derivative of this first part. So now I'm ready to take the derivative of the entire thing. So this guy's already done. I'm going to plug that in here, so that's what's in purple. And then I'm going to take the derivative of 2 sine x. And that's just 2 cosine of x, and this 2 cosine x and this negative 2 cos x go away, leaving me with y prime equals negative 2x times sine x as my derivative. Now let's talk about the quotient rule. So it's like the product rule where I have two different functions, f and g, that are both differentiable, but I'm going to divide them instead of multiplying them this time. So if I have f over g, this is the rule I'm going to use to find the derivative of that quotient. So it's the function g of x times the derivative of f of x minus f of x times the derivative of g of x, all over the square of my denominator, so g of x squared. So let's look at this example where I have a quotient here, so y equals 5x minus 2 all over x squared plus 1. I like to set up these problems much like the product rule problems, where I identify the numerator as f and the denominator as g, find f prime and g prime, and write out my little handy-dandy cheat sheet here. So that's going to be g times f prime minus f times g prime all over g squared. So let's plug it in and see what happens. Once I write everything out here, I just distribute and combine like terms. And just to note, this x squared plus 1 squared on the bottom, I'm going to keep like that just because if I expanded it, it's really not going to do much for me simplifying wise, so you can leave your final answer just like that. And here's a slightly different use of the quotient rule. So let's find an equation of the tangent line to the graph of f of x, so this is a quotient right here, at this point. So first what I'm going to do is rewrite f of x so that I don't have this 1 over x hanging out in the numerator. So I work it out just like this. So now I have f as 3x minus 1 and g as x squared plus 5x. I'm going to work through this same process, so let's see what we can do. This one's a little bit heavier with the algebra, but once I simplify everything and combine like terms after distributing this negative, which is really important, I end up with this equation for the slope of the tangent line, which is nowhere near done with this problem, so let's keep going. So next I'm going to take my derivative function and I'm going to plug in x equals -1 to find the slope of the tangent line, and that actually works out to be 0. So it's asking for the equation of the tangent line, so the slope is not enough. I need to plug in my y1 and my x1 into that equation. So I have that here in this point, which I'm very grateful that they gave to us. And I plug in 1 for y1 and -1 for x1, and I end up with y equals 1, which makes sense because that has a 0 slope. And looking at the graph, that is the equation of the tangent line at this point of f of x. And now I want to give a little plug for the constant multiple rule here. So there's a lot of functions that you're going to see that could look like the quotient or the product rule, but oftentimes you're just dividing or multiplying by a scalar, just a constant. So sometimes it's in your best interest to use the constant multiple rule instead of going straight for the quotient or product rule. So here are some examples. So like this first one here, it looks like a quotient rule, but it's just 6 in the denominator. So I can rewrite that as 1/6 right here. Same deal here. 8's in the denominator. That's like saying 5/8 times x to the 4th. And then here I can actually divide out this bit by x, leaving me with a constant of -3/7, which is easier than doing a quotient rule. And same thing here, I can rewrite this function so I can just use the constant multiple rule instead of the quotient rule. Always try to simplify, folks. And next up, let's throw in some more derivatives of trig functions. So these are just some basic rules if you are ever presented with a function that you need to find the derivative for that has either tan or cotangent or secant or cosecant. These are going to be the derivatives of those basic functions. So let's work out these two examples here. First one is pretty simple. Derivative of x is 1. Derivative of tan x is going to be minus secant squared x. And then our second one here is just a little bit more complicated because I have a product rule. So I just find f prime and g prime, plug them all in, and I'm able to actually factor out a secant of x. And so what I'm left with here is secant of x times the quantity of x times tangent of x plus 1. Our next example is one that asks you to differentiate both forms of an equation. So using a little bit of algebraic trig manipulation, I have y equals 1 minus cosine of x over sine x, which is actually equivalent to cosecant of x minus cotangent of x. So we're going to do the derivative of this guy separate from this one and see if they work out to be the same thing. First thing I do is set up my f and g and find my f prime and g prime, set up this thing here, plug in all the things, and what's kind of nice is that sine squared x plus cosine squared x, remember, equals 1, and so I'm left with 1 minus cos x all over sine squared x. So the reason that you might want to use and work through this form of y and use the quotient rule, which is slightly more complicated than just doing the sum or difference rule for the second part. You may be asked to write your answer in terms of sine and cosine, and that doesn't mean that you can't do that from the result of this guy, but sometimes it's just nice to start with sine and cosine and end up with sine and cosine, especially if you're asked for it. And now let's tackle the second side of this, so let's find the derivative of cosecant of x minus cotangent of x. So all I'm going to do is take the derivative of each thing separately and subtract this one from that one. And honestly, I could simplify it by pulling out a cosecant of x from this expression, but either one of these guys is fine. And I'm sure you're wondering if our last answer from the last slide matches this one in purple. It does, and here's the proof in blue. It does work out to be the same exact thing. And here's yet again another shameless plug to simplify. A lot of your simplifying could happen and probably will happen after you take your derivative. So here are some examples of what you might get after you differentiate a certain function, but honestly, you're going to want to simplify it so you can work with that further. And the last thing that we're going to talk about is something called higher order derivatives. So those are the derivatives that are called second, third, fourth, fifth, etc. derivatives. Now, you might see this in something that we talked about before called rates of change, and that's when we were talking about the position function, and velocity was taking the derivative of that position function. And if you actually take the derivative of a velocity function, you end up with an acceleration function. So this is what we call a first derivative, and this is what we call a second derivative. And there are a lot of different notations of this. So if you take a look at the first and second derivatives, you can kind of figure out the pattern. So y prime becomes y double prime, and dy over dx becomes d squared y over dx squared, etc. And let's do one final example, and that's to find the second derivative of this function h of x here. First thing I have to do is find the first derivative. So this is going to be a quotient rule. I complete it like we've worked through those other problems with the quotient rule, and I find my first derivative to be this quotient here. So notice that I expanded x plus 1 to the power of 2. I FOILed it out because I'm going to have an easier time taking the derivative of this quadratic instead of how this thing is written out. I actually need a different rule that I don't quite know yet. So I'm going to expand it out like this. And as you've probably guessed by now, in order to find the second derivative, you have to take the derivative of the first derivative. So let's work that one out. I'm going to need the quotient rule here, so I have my f here and my g here. I take the derivatives of both f and g, plug it into that equation that I have, work everything out. And a nice little simplifying trick here is that I rewrote this quadratic as x plus 1 all squared. So I can factor out an x plus 1 from the top and take out 1 from the bottom. So that tells me that my second derivative is going to be negative 4 all over the quantity of x plus 1 cubed. And that's going to do it for this video. Thanks for watching.